Hello everyone, welcome to the new session on data structures and algorithms. I hope you're following my channel. In this session, we will try to discuss about time complexity. We have seen in our previous sessions, like we have discussed many things, right? So as a part of data structures, we have seen some basic introduction and we have covered about data types, right? We got to know how important is this data type while you're writing your code, and we have seen range of each data type. We have practically seen how we can find out that range, and most importantly we have seen operators basically these operators will come as a part of your programming language, but we have discussed about operators to make sure that we write any code easily. So we have focused more on bitwise operators, right? So, and also we have seen some problems as well related to bitwise operators, like we have seen some coding problems on these bitwise operators. And of course, in our previous session, we have seen the importance of optimization, right? So how important is this optimization? We have seen like initially our code took 31 years and we have tried to reduce it to 5 seconds. It's very interesting, right? You can see my previous lecture, like importance of optimization tutorial. I have explained it in detail about this. You will get to know why are we basically optimizing our code snippets. And of course we have seen how we can handle the large data types, right? So these are the overall things that we have discussed in our previous sessions, right? So in this session we will discuss about time complexity. How important is this time complexity while writing any code, right? So let me scroll down, or let me remove this thing. Okay, right. So before discussing about time complexity, I just want to tell you, in our previous session we have discussed about time, right? Like we have seen it's taking 1 second, it is taking 5 seconds, and it is taking something like 31 years, right? So you have seen manually like how what is the actual time it's taking, right? In this session basically in data structures and algorithms, while writing any code snippet or while writing any algorithm, let's say in you know s- let's say specifically while writing any algorithm, we try to represent that algorithm in terms of time complexity. Okay, so there are different ways of representing it. Like we have big O notation, we have something like omega notation, like this, right? We will discuss about these notations in our next video, but in this video we will try to see how we can find out a time complexity from a code snippet. Okay, so let me scroll down. Let's say I given a code something like this. I've said avoid solve function. Okay, this is a function. Hope you have some basic idea about functions, right? We have seen in programming as well. So let me say I have written a function like int a equal to 1, b is equals to 20, something like this, and I've said long c is equals to 100. It's nothing new. Okay, we have seen about integer, we have seen about long, right? I'm writing the same things, and let me say I will write some for loop for I is equal to 0, and I'll run this for loop for 5 times. Okay, I'm not writing the exact code, just I'm trying to make it simple. Okay, so that each and every programming, it covers each and every programming language. Okay, so let me say I will say something like b plus c. There is some operations that are happening here. Okay, so this is the code that I have written. Now basically what happens is you will be given to find out the time complexity for this code. Okay, so what is the time complexity of this code? You can clearly check that these things are basic declarations and this is a basic operation. You can see a for loop here. In our previous video also we have seen that basically we have seen about iterations, we have seen about instructions, right? So let's not discuss about them, but let's only discuss about how many times this for loop is running. you can clearly check this for loop is running for 5 times, right? Now let me say if I change my n value to 10, my for loop will run for how many times? It runs only for 5 times. If I change my n value to 100, then how many times this for loop will run? It will again run for 5 times only. If I change it to 1000, then again it runs only for 5 times. So you can clearly check that this for loop or this solve function is clearly what? It is clearly independent of n. Whatever the input, right? Whatever this is basically input, right? So whatever the input that you are passing, it is not being used in this code. That means this code is doing some constant operation. That means it's doing the same thing repeatedly. How many times you call this function, but the code is doing a same functionality. Okay, so that's why we say it something like 5 times. Okay, every time it's running for 5 times. So we'll, in terms of time complexity, we generally say that it is something like big O of 1. Big O of 1. That means it is a constant time. It is a constant time. I hope you got to know about this word constant, right? So that's why we'll represent it something like big O of 1. You might be getting one doubt. Can't you write it as big O of 5? Yes, we can write it as big O of 5. But while writing time complexities, we make sure that we neglect the constant. That means whatever the constant, like it may be 5 times or it may be 10 times, whatever the value that you keep, we'll try to generalize it to big O of 1. That means a constant time complexity. Okay. So this code snippet will basically tell you about the time complexity and how much time complexity it's taking. It's taking a constant time complexity. Okay. So hope you got some basic idea about this time complexity. Let me go down. Okay. Uh, Let me write 2 more code snippets. Okay. Uh, let's say I write 2 code snippets here. I write the same code snippet again. Void solve. Okay. And here I've passed the integer value, and I'm saying something like for I is equals to 0 to n. Okay, and let me say some operations are happening here, like constant operations or whatever the plus, minus, or multiplication, anything. It can be anything. Okay, this is the first snippet. Let me divide it. Let me say I'll write one more code which is the same, like solve function having an integer value n. Okay, so here I'm keeping 2 for loops for I is equal to 0 to n, and I'm telling for j is equal to 0 to n. Hope you know this for loops, right? In programming we basically write something like this. These are 2 for loops, and I have one more for loop as well for, let me say, k is equal to 0 to n. Okay, and let me say here I have some operations and I'm closing it here. Let me move down. I'm closing it here. Okay, let me make it good. So there are some operations here and I'm closing it here. Okay, so let's look into this first one. Okay, in this first one you can clearly check that wait, here you can see this for loop is running for how many times? 0 to n times. Okay, that means the code is running for n times, right? The code is simply running for how many times? N times. Initially, in our previous discussion, we have seen that our code is running for how many times? 5 times. It is independent of n. Our code is independent of n. But here, if we take this new example, you can clearly check that the code is running for n times. So it's clearly dependent on n. That means dependent on n value. If you take n value as 10, then this loop will run for 10 times. If you take n value as 1000, then this loop will run for 1000 times. So clearly there is no specific value that we can say here. In the previous discussion, we have seen big O of 5. Like whatever could be the n value, we'll get big O of 5 only. But here, it's dependent of n. That means whatever will be the n value, that will be your time. So clearly we can state it here as big O of n. That means it's dependent of n. That's why I have written big O of n. Okay. So don't get confused about this big O notation. Okay. Simply think this as a function. Okay. Generally we will have functions in max, right? So think this big O as a function. In our next session, we will try to discuss about these notations. Okay. What are these notations and basically why do we need these notations? But in this session, we will try to discuss how we can, generalize the time complexity based on the input values. So in this, we got the time complexity as big O of n. So let's do the same thing for this one as well. Here you can clearly check that here there are two for loops, right? That means here you have this part and here you have this part. Okay, this down part. You have two parts here. That means you are going to get two complexities here, right? So here in this first part, let me say this is the first part and this is the second part. In this first part, you can see two for loops. That means for every I value, this for loop is running for n times. That means for I0, this second loop runs for n times. For I1, this second loop runs for n times. Similarly for In, that means whatever the input you give, it will run for n times. That means for any n value, it is running for n times. It is n into n. That means n square. Hope you got it, right? Generally, you could have seen while learning data structures, if there are two for loops, then you will blindly say that it's n square time complexity. Okay, but you need to see what are these variables. Okay, you need to see everything and you need to tell it as n square. And the first one is taking n square, right? Let's say let's see what does the second one will take, right? It's simple. It is taking n 0 to n. That means it depends on n. So it's taking n complexity. You can see that this solve function, basically if we write the time complexity as a whole, that means for this solve function, the time complexity will be something like this. Big O of n square plus n, right? But while writing time complexity, we'll try to normalize it to big O of n square only. That means we will neglect the lower order terms, just like how we have neglected 5 to 1 in the previous discussion. Like we have said big O of 5, right? But we have neglected it. That means we have normalized or generalized it to 1, right? So in the similar fashion, we will try to neglect this lower order terms. Neglect lower order terms. Okay, so I'll tell you with proof why do we neglect these lower order terms. Generally we have we can here there are two possibilities. Either you can say it as big O of n square or you can say something like big O of n, right? But we are telling it as big O of n square. Let us see the percentage of n in n square. That means we'll see the importance of this n value. That means hope you got it. We'll just see how important this n value in our code snippet. Let's say I'll give n value as something like 10, n value as 10 power 3 and n value as something like 10 power 4, and we'll see how much percentage does this n will take. N divided by n square into 100. I'm telling it as 100 because I want as a percentage. So if I substitute the n value 10 here, it will become 10 by 10 square into 100. That means these both will get cancelled. It is 10. So here the n importance is very, you can see it is very crucial because it's taking a big number. It's a good number, 10, right? Let me try to do for this. n divided by n square into 100. It's nothing but 10 cube divided by 10 cube whole square. That means 10 power 6 into 100. So here 3 here 3 times, and here we'll get what? You'll be getting 1 by 10. That means 0.1. So here you can see clearly n is having some least interest. That means it's having some less importance. We can say something like less. If I substitute n as 10 power 4, that means it becomes 10 power 4 divided by 10 power 4 whole square into 100, which comes out to be 100 divided by, here 10 power 4 will go for one time, and you'll be getting 10 power 4 here. So it's nothing but 10 square by 10 power 4, right? It's nothing but 0.01. Here it is very low compared to this thing, or compared to this thing. You can clearly see that this 0.01 is very low. So you can clearly see that if I increase my value of n, if I increase the value of n, you can clearly see n might become 0.0000, something like this. It may become something more also, something more, but you can clearly check that this n value is of least importance. That means we don't even need this n value, right? So that's why I'm telling we'll just neglect this n value and we'll try to write it as big O of n square, so that we will get a good time complexity, right? So while writing any time complexity, the important thing is we need to neglect the lower order terms, right? So coming about the discussion that we have seen in our video, in this video, we have seen big O of 1, we have seen big O of n, and we have seen big O of n square time complexities, right? So this is a very informative video, right? We have learned some good examples, like we have seen 3 examples, and we have seen why we need to neglect this lower order terms, and we have also seen how this code snippet is dependent on this n value, and how this code snippet is independent of n value. So if it is independent, then it's taking a constant time, which we will write something like big O of 1, and if it is dependent on n, then we are writing big O of n. If it is dependent on both n square and n, then we'll try to neglect the lower order term. That means we'll try to neglect the thing which is of least importance. N is of least importance. This, in this big O of n square plus n, this n is of least importance. That's why we have neglected it and we have written it as big O of n square. So in our next sessions, we'll try to take some big examples, and we'll also try to find out the time complexities for those examples, and we will also discuss about these notations, right? Big O notation, omega notation, like this, right? So we'll also see about them. Thank you for watching, guys. Hope you really like this content. If so, please subscribe to this channel and try to share it to your friends. Thank you for watching.